So I want to do something that I haven't been doing that I should have, is going over some homework problems that you had trouble with. All right, so here you may recall this homework problem. It says you have a matrix, and it says find all eigenvalues of M. Does M have two linearly independent eigenvectors? Is there a basis in which the matrix M is diagonal? Can M be diagonal? All right, so let's take a look at this. So I think that, actually I don't think I need this plugged in. So let's see what we can do with this. And just to get you in the mood here, we have M equals 2, 1, 0, 2. And then the standard way of finding eigenvalues, you want to solve M V equals lambda V. Okay. And that's the same thing as M minus lambda I times V equals 0. And that's a 0 vector. So if you take M minus lambda I, you get the lambdas on the diagonal. Okay. And in order for that to have a non-trivial solution, it has to be singular. Okay. So the matrix must be singular to have a non-trivial solution. Okay, so singular means the determinant is 0, right? So that's where you get the determinant equals 0. So that means that the determinant of 2 minus lambda 1 0 2 minus lambda is equal to 0. Now, determinant of that is you just use your 2 by 2 rule, and that says 2 minus lambda squared is equal to 0. So that means that lambda, there's only one solution, right? Lambda equals 2. Okay? All right. So, we only have one eigenvalue. There's only one eigenvalue. Okay? There's only one eigenvalue. Since there's only one eigenvalue, that means there's only one eigenvector. Okay? So that means that there's not a basis of R2 that consists of eigenvectors. Okay? No basis in R2 consisting of eigenvectors. Now you need eigenvectors for the matrix to be diagonalized. So that means that M is not diagonalizable. Okay? So, what is wrong with this argument? This is not correct. This is not correct. So it's important you pay attention because a lot of people did this. This is not a correct argument. Where did I make the conceptual leap? All right. Certainly the matrix has to be singular. Certainly singular means that the determinant has to be 0. Certainly there's only one solution for lambda. Certainly that means there's only one eigenvalue.
It's between the no basis and M not being diagonal.
Well, in fact, that's not where the problem is. In fact, you do need to have a basis of eigenvectors to make it diagonal. Have to what? Okay. Well, yes, you only have one eigenvector, right? Okay. So, in other words, you're saying the argument is correct.
But no, you have one with a multiplicity of 2? Is that what?
But you don't have two.
Well,
you don't have two
you have
unique
one. All right.
eigenvectors.
Right. You cannot go from here to here. That is not true. Not true.
Okay.
I'll give you an example. Very simple example. Okay, so this is important. A lot of people did this. Okay. Okay. So I should make a big red X where it's not true. Enormous red X here. This is not true. It's not true that one eigenvalue means one eigenvector. Okay. And here's an example. 2, 0, 0, 2. What are the eigenvalues? Okay. Okay. The eigenvalues, we do the same thing. 2 minus lambda, 0, 0, 2 minus lambda. If you take the determinant, that says that 2 minus lambda squared equals 0. There's only one eigenvalue. How many eigenvectors? What's the eigenvector?
How many eigenvectors? Or there's y. Say y equals y. So
How do we find the eigenvectors?
be 1, 0, 0, 1.
Find the eigenvectors.
There's 2.
Okay. How do you find the eigenvectors?
You plug the lambda back into
You have. That's right. You need to plug the lambda back in.
You get zeros all around, so x would equal x and y would equal y. So you get 2 vectors.
And solve, right? All right. Okay. So you're going to get 2 minus lambda is equal to 2, right? 2 minus 2, 0, 0, 2 minus 2. That's times v equals 0. So that says 0, 0, 0, 0 times v equals 0. And what solves that?
1, 0, 0.
Everything.
Everything.
Anything. Free for all. But since var2 is two-dimensional, there are 2 linearly independent eigenvectors. So all vectors are eigenvectors. Okay, so that means there are 2 linearly independent. Okay, why is everything an eigenvector? Actually, you don't even need to think about, you don't even need to solve this. If you have 2 times the identity, and you apply that to any vector, what does it do? If you have 2 times the identity matrix and apply that to a vector,
It's 2 times.
you multiply the vector by 2. Whatever vector you want. That's what eigenvalues do. They stretch your vector. So it's not true that one eigenvalue means one eigenvector. Now it turns out that if you did try to solve for that matrix that I gave, there's only one eigenvector. But you had to go through that to determine that that's true. You can't just say one eigenvalue, one eigenvector. That's not correct. Okay. All right, so let's see. All right, so let me look at number 6. All right, number 6, people did this one. So let me copy this. Oh, sorry, I have to do this first. Okay, so there's this one. I think you may remember this. So here it says, a projection is a non-zero linear operator P such that P squared equals P. Okay. All right, so now we want to find, let's find the eigenvalue. Whoops, let me make it blue. You don't need to be so screamingly. Okay, so I want to find the eigenvalues of P. So what you want is, so what that's going to be is you're going to want to find P, let's see. Well, you want to find PV equals lambda V. So that means that, how did we do this? I don't remember. So multiply both sides by p squared v equals lambda times pv. All right, so that's going to be true. Let's see. No, I'm sorry. It's, well, that's true.
Yeah.
That's true. So then that's saying that what? That's saying that,
P times v equals lambda pv.
well, what you have here now is that, since p squared v is equal to p squared is equal to p, I can replace that with p minus r. Okay. So that means that pv equals lambda pv. Or I think that what did people do? I don't remember what people did. They didn't do it quite that way. Okay, but I'll do it this way. I'll just do it this way. This says, but p squared v is equal to pv, so pv equals lambda pv.
Right.
Okay, so that means that lambda must be, that either lambda is equal to 1 or pv equals 0. So either lambda equals 1 or pv equals 0. Now, PV is equals 0 is the same thing as saying the eigenvalue is 0. Okay. So I have a non-zero eigenvalue. So that means that lambda equals 1 is an eigenvalue for P. So that means that P has a non-zero eigenvector. Okay? What is wrong with this argument? This argument is not correct. Not correct.
Because you just solve for an eigenvalue, you haven't solved for an eigenvector.
I'm not solved for an eigenvector. This argument does not work. And I'll show you why it doesn't work. Because I could put in P equal to the 0 matrix. And all of this would be true. Right? So let me get my big red X out again. This is not true. It's not true. Okay. So, and I'll show you why not. Example, let P equal to the 0 matrix. Okay. Then it's true, isn't it, that you have P squared V equals PV for any V. Isn't that correct? That's still true, right? Because you get 0 on both sides. Okay, for any vector v. So I can use that argument, that same argument, and so I can also get PV equals lambda PV. Now, why does the argument break down here? This looks like it means what lambda is equal to 1. Why does it break down? I mean, you just cancel PV on both sides, right? Why does it break down? This is true, isn't it? If my P is this, right?
Right, that works too.
This is true, isn't it? Right? So for any eigenvalue, this must be true. So why doesn't this imply lambda equals 1?
And that with P equal to 0, lambda could be any.
All right, but that's true. But why can't I conclude from this equation here that lambda is equal to 1? Why not?